This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Welcome. I'm going to be walking behind your backs, by the way, because these people, travel far. But I'm going to walk in front of you too. In the back there is Neil Lowe, who is going to be recording these lectures. Okay, so say hi to Neil. Hi. And I am George Arau, and I am going to be teaching Essential Maths 2, Calculus, or Foundation, right? Foundation Mathematics 2. They're the same course, they have different names. I don't know why. Okay? I learned, just today, because I'm a very disorganized man, I learned today that when you set up the website for one of them, it doesn't automatically mirror to the other one. So if you are in Essential Mathematics and you have access to the website, you will have access to what I'm going to show you now. But if you're in Foundations, you don't yet because I didn't have time to do the mirror, but you will. All right? So who is in Essential Maths? And Foundation? One. Sorry, I didn't mean to laugh at you. With you, more like it. Okay, so let me guide you through the website because from my end, it looks like this. And you have a course outline here, which will detail, the bureaucracy of a course. But so you don't tell me, you didn't know about it. I have hard copy for you. If you lose it, you can go to the website and retrieve one. And it does say Essential Maths, although it's the same for the other one. Welcome. You don't have to look at it right now, but it has all sorts of information like when our assignments due, when I'm going to collect them, when I'm going to give them out to you, how many assignments, quizzes, final exam. Well, we don't have a date yet, but some information is there. What type of things are going to be in these assignments in the final, which graduate qualities that we're measuring with everything, that sort of information, okay? Is there anyone here who is new to the university? First time?
Oh, I've been here a couple times for orientation.
No. First, yeah, welcome. Okay, welcome. So you guys don't know anybody else? You guys know each other? You guys know each other? You know each other? No? No? Okay. If you do know each other, if you do know someone else, it really helps if you work with them. Perfectly fine. Encouraged to work with someone. But when you turn in your work, do it yourself. Okay? You can talk as much as you want with someone else and go, how do you solve this? And they tell you, you tell them, not a problem. But when you have to write down the final copy of your work, tell them to go home. Okay? And you do yours separate from them. It's very important. Let's see. Let me show you the website for the course. It's over here. Learn online resource. That's my end of our website. So I'm going to put it, switch role to student. OK. That's me. All right? I'd have to find a picture, and it was kind of hard to find a picture. I don't photograph very well. So this is what we're going to be doing for the first week. We don't meet for tutorials this week. So our tutorial is usually on Thursday, right? And but we don't meet this week. So for next week, you could take a look at these exercises here. There's some additional ones from this book. Some of you may already have the book. Do you? Do you? No? The book should be available at the bookshop here. So, just take a look. Sham outlines are very, very good. I think they're very nice and plenty of exercises. And we're going to go through as many as you want. Do you know Judy Black? Yeah. So Judy taught Essential Maths 1, and she used to teach Essential Maths 2 as well. A lot of what I'm doing is based on what she's already done. And very shameless of me, I borrowed her formula sheet, and I put it in here. So if you want to have that while you're working, that's just a guide that tells you, look, these formulas are the formulas you generally need to work with. And I'm going to be posting these things regularly every week. Okay? And sometimes it's going to be in advance as well. So if you're really keen, you can go to the website and see what's going to be done in 2-3 weeks and start doing it. I doubt you'll do it, but it's there for you. I'll scroll down so you see that the website is very naked at the moment. Hi, welcome. I have this thing that I do whenever people tape my class, that whenever someone arrives late, I let them in the picture. Look, I arrived late. But there's absolutely no problem. You can arrive as late as you want. Yeah, I don't want to go. Okay, so the rest of the website at the moment is blank, okay? But I'm going to be adding very soon to it. All right? Do you have any questions? No? Why not? Why not? Can I use a calculator in the exam? That question, I mean, come on, you have that question, right? Yes, you can. Any calculation, any calculator. No, not any calculator, for instance. The iPhone? No. Lovely. Okay? The iPhone has a calculator in it, but you cannot use it. Yes. That one is all right. If you need to know if your calculator is okay or not, ask me.
Here's a graphics calculator.
I don't think a graphics calculator is allowed. If it thinks it's not allowed, okay? A scientific calculator is what we aim for. It's happened before, so I'm going to say this because I always say it. You have to learn how to use a calculator before the final exam, because the day of a final exam, you are there, you take it out of a plastic. Believe me, it happened. It happened last year. And then you don't know how to do something, and you ask me, and I have no idea. I don't own a calculator. And even if I did, it's one of hundreds that are available, and I wouldn't be able to help you as much as I would like to. Okay? So if you're going to buy a calculator, if you're going to do anything like that, learn to use it beforehand. Okay? learn to use it beforehand. Any more questions? No? George, where were you born? That's a question I get a lot. Yes. I was born in Rio de Janeiro. Yes. But I normally make myself understood, so I hope you have no problem. And you? Where were you born?
Bangladesh.
Bangladesh. I see. There you go. Really? Yeah. Yeah. Where?
Dhaka.
Dhaka. Have to go there. Okay? If you have any questions, you can just ask. You can just ask. How long since you've taken any maths course? Last semester? Last semester? Was it Essential Maths 1?
Yeah.
Not with Judy?
No, it's Ross.
Oh, Ross Frick. If that camera weren't on, I would say something, but I will say, Ross should be made into a statue and preserved forever. He is great. I also do a pretty good imitation of Ross Frick. No, not today, not today. You have to earn it. You have to earn it. Okay? We've been working together for a long time. Were you also in with Ross? No? So when did you last?
Probably a year and a half ago.
Okay. Look, the key to understanding mathematics is not having fear to ask. If you don't understand, just say, I don't know. And I'll try to provide more explanation as much as I can. Sometimes it works. Sometimes I'm going to ask for help. I'm going to say, well, look, does anybody want to have a go at explaining this? And it's perfectly fine. Okay? Sometimes, in fact, a lot of times, one of you will get a better understanding of a question than I do. Okay? Why do you need this course, by the way? What's your program? What's your program?
Doing OEPM, so teaching.
Teaching? 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 Science?
Engineering.
Engineering?
Teaching.
Teaching?
Engineering.
Engineering?
Teaching.
Engineering. Teaching.
Okay. Well, there are like just a few. Science, teaching, engineering, so we can work with that. If you want to see anything geared towards your field, okay, we can put examples here for you. All right? In fact, I think pretty much science and engineering, it's like a knee-jerk reaction that I put examples. I have to remember to put some more examples for education as well. But I will. Okay? All right. Okay. Do we still need this? No, we don't. Not today, unless you want to ask a question about the website. No? All right. I'm sure I'm going to remember something. Shut down. Restart. Off. Neil, you're really, I mean, this camera is really doing something with my style here. Anyway, all right, let's start. Do you know what calculus is? Have you heard of, because this is calculus, right? So what's it all about? Why calculus? The fact is that in science and engineering, you can't do a thing without calculus. I mean, engineers will say, yes, you can. And it's true, they can do a lot. But more and more, you need calculus. You need calculus to see if the building is going to fall or not. You need calculus to see if the electrical system is going to work or not. There's just no getting around the thing. Okay? What is calculus? What can it do for you? From a maths point of view, it's a bunch of equations, and you can do something with the equations to do. It's very dry. There's no meaning. Calculus has no meaning by itself. It's something about equations and numbers. It's another discipline, science, physics, or engineering, or economics, or biology, who need to answer a few questions, and they look for the available tools, and they say, oh, look, there's this thing here called calculus, and maybe we can use this. And they've been very successful in doing that. Don't blame me, okay, even though you can. But it's that thing, right? Every discipline, they look at what's available out there and try to use it. Mostly, the questions that calculus will help you with are questions that go along the following lines. Okay, I need to build something, and I need to make it the best possible. The one that gives me the most for the least money. Whatever, something like that. Calculus is good at answering that particular question. Okay? There was a time, 25 years ago, that early, that calculus would help you to draw pictures. It would be a great tool to draw pictures. You don't need that anymore because graphing calculators and computers, boom. We're going to do a little bit of picture drawing here in the course as well because tradition dies very slowly. Okay? But certainly, I wouldn't say it's one of the prime applications of calculus. For the people in education, that may be interesting, though. Okay? Because it gives you a way of relating all the equations to the geometry. All right? Since I mentioned geometry, I'm going to go back to before calculus. Anyone has any idea when calculus was invented or developed? Okay. Yeah, go.
Two guys came up with it.
Two guys came up with that, yes.
Differently, that's what I remember.
Kind of at the same point in time. One of them was English, the other was German. But when? Okay, 1900s, 1800s, 1700s, or 1600s?
1900s.
Earlier. It's old. Yeah. It's from the 16th to the 17th, 17th century to the 18th century. So it's old, okay? It's old. But it's been developed for all this time. Everything you're going to see in this course is at least 300 years old, okay? It's not that we're teaching old stuff. The thing is, it hasn't been improved upon yet. Okay? The guys who came up with that 300 years ago, 300 odd years ago, they did such a great job that we are still using those tools. And for the foreseeable future, in the next 200 years at the very least, that's my personal opinion, we're going to still be using calculus and doing exactly what you're going to see here. It's that good. But I want to talk before calculus. Before calculus, and that's where I want to start my story, there was this one guy called, he was French, called René Descartes. 1600 and something. And he was in a war, in a battle, and he got injured. They put him to heal somewhere. And while he was there, lying down and doing nothing, he came up with these great ideas, wrote a few books about it. One of his great ideas was this. There is a way to connect the old geometry from the Greeks, and when I say Greeks, I mean BC, okay, to what was then, at the time, the modern theory of algebra. Just at the time of Descartes, you could say, oh, I want to study circles. And all you could do was draw a circle pretty good. I missed the center though. Draw a circle and, get straight edge, compass or whatever, ruler. And, if you want to answer a question like, okay, you draw a line here, and let's say this radius here is 5, okay, and you go 2.5, you go halfway on the radius, and you draw this perpendicular line here. Well, what's this distance from here to here? And you had to do geometry by, looking at triangles and Pythagoras and whatnot. There was no other way. On the other side, over here, there was something called algebra that had no pictures associated to it, none at all. It was just equations. So you could write something like this. Or you could write something like this. And again, this was recent compared to the geometry of the Greeks with a circle in there that was thousands of years old. The stuff of writing equations like that was 100 years old by the time, or 100 and some years old by the time of Descartes. So it was very recent. Not everybody knew about it, not everybody cared about it, and there was no application. Geometry had an application. Okay? If you want to demarcate land, you needed geometry. But there was no application at the time for those equations there. I don't know about you. Is it automatic to you these days that if you see an equation, you know that there is a picture associated to it? Because that's Descartes' great contribution. Okay? His great contribution is that every time you see a picture, you can replace it by an equation, the equation for that picture. And every time you have an equation, you have a picture to go with it. The advantage of that is, there's a huge advantage. It's much easier to deal with equations than to deal with pictures, believe it or not. Okay? The picture is very intuitive. But I don't know if you ever had that feeling that if you see how to do it with a picture, it's great. But if you don't, you're going to be there for a while. Whereas with the equations, you can write down a few rules that a computer can follow and get to the answer. Okay? So once he had that insight, and I'm going to talk about the insight right now. Once he had that insight, a lot of stuff that used to be done just by geometry started being done with the equations instead. And then once you get the result from the equation, you move back to the geometry and you give a geometric reply to the question you started with. Okay? How do you manage a dictionary between picture and equation? So his idea was this. It's the idea you know already. Latitude, longitude, if you look at a globe, okay? If you give a latitude, you're going one way, longitude, you're going the other way. I hope I got these two right. It's the same thing, but you're not on a globe, you're on a flat. He said you put a special line there that you're going to call the x-axis. And you put numbers on it. Here is what I'm going to call 0. And there's going to be a unit, okay, which is totally arbitrary. But I'm going to put it here. This is 1. That's 2, 3. And if you move to the other side, -1, -2. And then you put another axis perpendicular to that one, the vertical one, and you call it y. My voice is very soothing, so you're going to feel tempted to sleep. And when I see you sleeping, I'm going to say, sleep, sleep, sleep. I'm still trying to make someone actually sleep, but okay. The vertical axis is going to be called the y-axis. 1, 2, 3. Does that squeak in the camera? A little bit? How about this? This is -1. You should do this to scale, of course, but I'm not the Rembrandt of mathematics, so. Okay. And now every spot on the plane where you do geometry is going to be identified by 2 numbers, which are called the coordinates, right? So you're putting geometry onto something that can be labeled by 2 numbers. The first number, you call it x. The second number, you call it y. And all of a sudden, an equation shows up, the relationship that you have in that picture between the x and the y. So if you draw a line like this one, and pretend it's a straight line, okay? Pretend it's a straight line. In fact, I'm going to help myself here, a little poetic freedom, if you will, and I'm going to move a 1 to this place. Okay? If I draw a straight line there, which is a perfectly good geometrical entity, okay, all of a sudden it will generate on the other side a perfectly good algebraic entity, an equation. And that equation is going to be very specific to that line. In fact, the equation for this red line here is that. If you're comfortable with that, great. If you're not, then we'll talk later. Okay? One of the things that Descartes showed is that it doesn't matter which straight line you're talking about. They all have kind of the same shape. They all look like this. AX plus BY equals C. A, B, and C are numbers. So in here, if you take a look, the A is equal to 1, 1x plus 1y is equal to 1. A, B, and C, they're all 1 in that. Okay? I'm not going to justify that because that's stuff from Essential Maths 1. But if you need any help with that, we can talk about it either in my office time or during tutorial. Is this old hat to you? You've seen this before? Yeah? But perhaps not as well explained. No, sorry. Okay? Now, everything is beautiful. Theories are beautiful. But the practice of a theory is something else, okay? All right? So you have to be careful. You have to be very careful because, as I said, every line that you draw has an equation. Every line that you draw has an equation. This line has an equation. But it's likely to be the worst equation you've ever seen. And who cares? No, these are important. Who cares? It's not just because you're doing mathematics that, it's going to be totally abstract. We don't do abstraction in mathematics if you don't have to. Abstraction is bad. Okay? You do care about the equations if they're useful. Straight line, very useful. Okay? What else is useful? That? No. Okay? Likewise, on the other side, you have the same thing for equations. You can write any equation you want. Any equation you want. Y cubed plus x squared minus 3 divided by 7y plus 3x minus 81x to the power y to the power 36 sine divided by the log of y divided by x. Yeah, okay. And who cares? You can always write, oh, by the way, that's not an equation. Equal that to 0, okay? You can always write a complicated expression. And it doesn't mean it carries any weight in real life. So, change my mind. So, which ones are important? The ones that are important are the same ones that were important to the Greeks. Okay? They are the straight line, the circle, the ellipse, the hyperbola, the parabola. That's it. Okay? Those are the ones that we care about. Oh, George, you're lying to me. There must be more. Yes, I'm lying to you. There are a few more, but you have to understand these first. Okay? Now, each one of them is connected to something that's actually useful and important. Okay? I'm not going to make a case for the straight line, but I will make a case for, say, the parabola. If you ever try to get an antenna for external signal at your place, not one of these wire antennas that the birds sit on it and then you never get a reception. I mean a satellite dish. That is in the shape of a parabola. Why?
That's how waves travel.
Because that's how waves travel. You're getting there, yes. There's something to do with the way waves travel. Why? No? A few years ago, an American, it's always an American, had this brilliant idea of, do you smoke? Nope. Had this brilliant idea to make a cigarette lighter that doesn't use fluid. How? It turns out that the parabola has this beautiful, beautiful, brilliant thing about it. Do you know what the shape of a parabola is? He said, that's him, he said. Okay? That's the shape of a parabola. Right? It is somebody doing this. Right? The parabola has a shape like that. There's a special point in the parabola, somewhere here, called the focus of a parabola. And the amazing property that the parabola has is, if imagine this is a billiards table. Okay? It's billiards, green felt, lovely, parabolic. Okay? If you hit the ball from here, straight down, it will travel here, it will bounce, and it will go there. Or what if you take a different ball and hit it straight down? It will come in here, bounce, and it will go there. It's like the that spot, okay, really likes to attract every bouncing off the sides billiard ball. That's called the focus. That's why it's called a focus, right? Because if anything travels this way on the parabola, it goes and focuses down there. So if you have waves coming from a satellite traveling towards the parabolic dish, it hits the side and then gets focused in that one spot. So you can have a very weak signal, very weak, but because it gets concentrated on that spot, you kind of obtain free magnification. And that's why every antenna is parabolic. And what this guy wanted to do with a cigarette lighter is to produce a parabolic cigarette lighter that you aim it towards the sun and you put the cigarette so that the tip of the cigarette is right here. So the sun rays come in here, concentrate there, and lights the cigarette. I've seen it. It works. But you need to have a sun to have a smoke, and so it didn't sell. And the Greeks somehow were interested in that. The ellipse is just like the parabola, but there are two. What does the ellipse look like?
Isn't it an oval?
It looks like a flat egg. An egg that you kind of set on top of a bouncy ball. You know, a bit flat like that. The ellipse is just like the parabola, but it has 2 points. And whenever you say something here, it bounces off the walls, and somebody else can hear it over there because it focuses from one to the other. The whispering wall up the road in the Barossa is an ellipse. So if you go to the one side, have you done that? You go to one side of it and you whisper, and somebody on the other side will hear you perfectly. It doesn't matter how little you whisper. That's what's going on. Each one of them has an equation. So I want to tell you right now what are these equations for these important, historically important, but also important for modern day engineering. Okay? And if you're teaching, these are great examples, by the way. Okay? Important for modern day engineering. How do you get from the I need a drink of water. From the geometric image to the equation, okay? I'm not going to do every single example. I'm going to do the circle, though. All right? Each example is slightly different. But if you see how the circle works, the circle is what? You have a center. And you have a radius. And if you think that the radius is a piece of string, I happen to have a piece of string right here with me. And you put your finger on the center, and you go there, and you go around. And you go around. You make a circle. So the circle is not the center, but are the points that are at the same distance, radius, to the center. If the radius is 5, that distance is 5. The question is, the million-dollar question is, how do you change from that picture to that other equation? Here's what Descartes did. First thing he did is he put the center right here. So that's the center. It's arbitrary. You could have put the center anywhere you want. But start with the easiest. Put the center right at the 0, 0. You say that 0, 0 are the coordinates of a center. And then you come in here. Let's say radius 5. Radius 5 is OK? So this guy here is the point 5, 0. It is in the circle because it's distance 5, right? Distance 5. I can tell you 3 more points that are easy to find. They're also distance 5. There's this one here. What's the coordinate of that? Interactive class. Good. 0, 5. Negative 5, 0. And let's go over there. Yeah, go. 0, negative 5. These are the 4 easy points, and I apologize right now for not having to scale because, but you get the idea. It's the other points that are hard, right? The other points are the ones that are weird. The ones that should be somewhere there, and this should be a circle, by the way. Okay? So here's what Descartes does. He says, okay, pick a hypothetical point. This is x, y. I don't know what x and y is. It's hypothetical, right? They are variables. Okay? What do I know? I know that this distance here, I loved it. I just did, is 5. And then he filled up a few other lines that are not in the picture, but he placed them there. He put this vertical line here and this horizontal little bit here. And he noticed that he has a right triangle. And as soon as you see a right triangle, your knee goes, boop, Pythagoras. Because it's a knee-jerk reaction. And in that picture, the hypotenuse is 5. And this leg here is x, and that leg there is y. And Pythagoras tells you that x squared plus y squared has to be equal to 25. And that's the equation of a circle. Nobody knew that before Descartes. You can imagine that it is really a step forward, okay, to be able to put an equation to a picture. Before Descartes, if you wrote this and you wrote a circle of radius 5, two completely different things. After him, they're the same. Again, just to repeat myself, what it gives you is a new way to study geometry by using algebra. It's not a new way to study algebra. It's a new way to study geometry. It turns out that, of course, every free way is two-way. And you can also study algebra if you know the geometry involved, but let's not go there. Okay? It's not the point here. We want to study geometry. What happens if you change the center? What happens if you change the radius? Here's what happens. I'm going to leave this for you to puzzle out, but it's very similar. And if you've seen this before, it's going to flow like poetry from your pen. What happens if you put the center not at the origin where it was, but here at A, B? And what happens if the radius is not 5, but it's r? I'll tell you what happens. What happens is this. You have to pretend that AB is the center. And you put this picture, but over there. Okay? Where's the triangle? Where's the... Now, it would be an incredible aid to teaching if one of you could come to the whiteboard without feeling, oh, I'm so nervous, I'm on camera. But since nobody volunteers, this triangle here has to be there. Yeah? How about a laser pointer? I'll bring a laser pointer so you don't have to walk over there. Okay? Memo. Buy laser pointer. But there is a picture here. Right? There is a triangle just like that in here. And it lives here. Okay? So now, remember that this used to be x. This used to be x. It's not x anymore. It's x take away a. Because it's how much extra you go from a, x minus a. Likewise, the horizontal is y take b. And the hypotenuse is r. So the equation is that. Check that out. Write it yourself in your own words. Convince yourself that that's true. Okay? Oh, it's lunchtime. 10 minutes break. We'll be back.